Good morning. I'm Dr. E. Kavita, working as Assistant Professor in the Department of Chemical Engineering, SRM Institute of Science and Technology. I welcome you all for the experiment Heat Transfer by Natural Convection. There are three modes of heat transfer. They are convection, convection, and radiation. When there is a temperature difference between surface and fluid, heat is transferred by convection. There are two types of convection. They are natural convection and forced convection. What is natural convection? How heat is transferred by natural convection? I'll explain with an example. Let us assume a vessel with water and the vessel is kept over some heating source. From heating source, heat is transferred to vessel surface. And through the vessel surface, heat is transferred by convection. So the molecules having high energy will impart energy with molecules having lower energy. So due to the movement of molecules and due to the carryover of energy, heat is transferred through the solid media by convection. Then from surface of the vessel, heat is transferred to fluid molecules adjacent to it. Once the molecules receive heat, it will become lighter. So lighter molecules will tend to move in the upward direction and denser molecules will try to move in the downward direction. So fluid flow current is generated and heat is transferred to entire mass of fluid medium. So natural convection is the transfer of heat due to movement of air molecules or movement of molecules, fluid molecules without any kind of external force. Natural convection occurs due to density difference which is created due to temperature difference. And here buoyancy force plays a role. So the density difference or the changeover in density exerts a buoyancy force which results in the movement of fluid molecules over the surface. So that is called natural convection. Natural convection is also known as free convection. So the flow velocity encountered in free convection is much smaller than that experienced in forced convection. So what is that forced convection? In this example, if I place a stirrer and continuously stir the mass of fluid, flow current is generated due to this external force that is created by the stirrer, and heat will get transferred to entire mass of fluid. So due to the external force, flow current is generated and the heat is transferred. This mode of heat transfer is called forced convection. What is the aim of the experiment? To find out the natural convection heat transfer coefficient by performing the experiment in a vertical heated tube which is transferring heat to ambient air. Let us move on to description about the experimental device. Experimental setup consists of a rectangular duct which is open at the top and bottom to allow air freely over the cylindrical pipe which is placed inside this rectangular duct. The cylindrical pipe is connected with the heater, and heat input to the heater can be adjusted with the help of voltmeter and ammeter. So when you switch on the main and from heater, heat is transferred to cylindrical pipe. Once the surface becomes hot, heat is transferred from the hot surface to ambient air. So it will get transferred to air molecules adjacent to it. So the air molecules will become lighter and denser molecules will try to move in the upward direction, and the lighter molecules will try to move in the upward direction, allowing the denser molecules to enter into the duct. So heat is transferred to air molecules which is flowing across the cylindrical pipe. So the temperature across the pipe surface and also air temperature can be measured with the help of thermocouples, and here we are provided with a digital temperature indicator. So with the help of this, temperature across the surface and ambient air temperature can be noted down. So the temperature data and voltmeter and ammeter reading you need to know that. Now let us move on to procedure. How do we perform the experiment? So in the experiment part, Once you switch on the heater, from heater, heat is transferred to this pipeline and the temperature of the surface becomes higher than the temperature of air which is flowing across it. So from hot pipe surface, heat is transferred to air molecules flowing across it by natural convection. So first you need to switch on the main and adjust the heat input to heater by adjusting the thermostat position. Next, you need to note down the temperature across the pipe surface and also ambient air at 5-minute time interval until the system reaches steady state. How to identify the system has reached steady state or not? Once the system reaches steady state, rate of heat transfer, that is a net rate of heat transfer becomes zero. So you'll get constant set of temperature data. Once you arrive at the data, you can start performing the experiment. Next, let us see how to tabulate the experimental data. So first you need to note down voltmeter and ammeter reading. So B refers voltmeter reading and A refers ammeter reading. The next tabulate the temperature data. T1 to T5 refer temperature across the pipe surface. TA refers ambient air temperature. So this set of temperature data you need to note down at 5-minute time interval until you get constant set of temperature. Once you arrive at this temperature, you can stop performing the experiment and steady state temperature data to be substituted in the formula for finding the required data. And TS refers average surface temperature. So average between T1 and T5 will give you TS. TF is the film temperature, that is the average between surface temperature and ambient air temperature. Next, we'll move on to calculation. There are two major calculations: experimental value of heat transfer coefficient and empirical value of heat transfer coefficient. So first, I'll explain about the calculations on experimental value of heat transfer coefficient. By Newton's law of cooling, rate of heat transfer can be written as HA delta T. So in this expression, so Q refers rate of heat transfer, H is heat transfer coefficient, A heat transfer area, and delta T is the difference of temperature between surface and fluid. So we can assume that rate of heat input to heater, that is equal to heat transferred to pipe surface. So the rate of heat input to pipe surface, that is heat loss from pipe surface to air, that can be calculated by using the formula V into I, where V is voltmeter reading and I is the ammeter reading. Then area A can be calculated by using the formula pi dl, where d is the diameter of the pipe and L is the length of the pipe. So here you are given with the specifications data. With the help of that, you can calculate area. Then TS, TA. So TS is average surface temperature. So average between T1 and T5 will give you TS, and TA experimentally found, that is observation data. By rearranging this expression, you will get the heat transfer coefficient experimentally found value. So Q can be calculated from V into I. A is through pi dl, Ts and Ta. By substituting all these values, you will get experimentally found value of heat transfer coefficient. The next calculation is empirical value of heat transfer coefficient. With the help of Nusselt number, we can find out heat transfer coefficient empirical value. For the calculation of Nusselt, you need Grashof and Prandtl. Based on the value of Grashof and Prandtl, appropriate equation can be used for finding Nusselt number. So how do we find out Grashof number? Grashof number, that is calculated with the help of the expression beta G LQ delta T by gamma square. Beta is coefficient of thermal expansion, G acceleration due to gravity, L is length of the pipe, delta T is the difference in temperature of surface and fluid, and gamma is kinematic viscosity. So the property data involved in this expression can be obtained from data book at film temperature. As I mentioned earlier, film temperature is the average between surface and fluid. So first you calculate this average temperature, and at this temperature From data book, note down the property data. Kinematic viscosity, Prandtl number, thermal conductivity of air, coefficient of thermal expansion, that is inverse of film temperature, and the film temperature to be substituted in terms of Kelvin. With the help of all these data, Grashof can be calculated. By substituting Grashof and Prandtl in appropriate equation, you will get Nusselt number. The Nusselt number can be written in the form of HL by K, and H is heat transfer coefficient, L is length of the pipe, and K is thermal conductivity of fluid. By rearranging the expression, you will get empirical value of heat transfer coefficient. The next calculation is local heat transfer coefficient. So here you are given with the formula for finding local heat transfer coefficient, where Q is rate of heat transfer, A is the heat transfer area. In this case, what point you need to measure the local heat transfer coefficient, that particular length to be substituted for finding heat transfer area, and Ti, Ta, and Ti is the local surface temperature, which is ranging from T1 to T5, and Ta is the ambient air temperature. So by substituting these data in terms of length in heat transfer area, you will get local heat transfer coefficient values that can be tabulated here. Then you can plot the graph between local heat transfer coefficient and length in order to find out what is the changeover in local heat transfer coefficient with respect to distance. Then next, tabulate the results. Tabulate the value of experimentally found heat transfer coefficient and empirically found heat transfer coefficient. Thank you all for listening. Thank you.